broadcasting. Yeah. Okay. Good morning, everybody. I'm Alex Hills with Carnegie Mellon University, and my co-presenter is my colleague, who I think some of you know, Jens Monk, who runs the Double E department. You're the big boss, right?
Oh, gosh, no.
And so we've been working together on what we think is some pretty interesting stuff. So welcome to all of you. It's about satellite communication, which just like a lot of other technologies comes with benefits, but it also comes with some challenges. So you won't be surprised that we're working on the challenges, right? But satellite technology is not new in Alaska. In fact, we used it 50 years, more than 50 years ago, back in the 70s and 80s to connect the villages out there. We used what we then called small earth stations. That's a 15-meter diameter dish that was really state of the art at the time. That was, earth stations back then were much bigger. But that's a 4.5-meter antenna. And we were the first place in the world to use this technology to connect people scattered out across far distances. I actually wrote a book about it that some of you might have read. It's called Finding Alaska's Villages and Connecting Them. But several years later, after we did that, I happened to meet the communication minister of French Polynesia. That's Tahiti and smaller islands that cover a huge area of the Pacific Ocean, an area that's roughly the size of the land area of the state of Alaska. And so this was several years after 1975 when we started this. And he told me that in French Polynesia, they had a great idea. They were going to use small earth stations, and they were going to be the first place that had done it. And I said, well, yeah, I've heard of that technology before. Anyway, one thing to point out about this antenna or any other satellite dish antenna is that its whole purpose in life is to focus a beam, right? To point a beam in a certain direction. And so that the shape is a parabola, and that's, a lot of you probably know, that's the shape that does the job. We put those in over 100 villages across the state, in places like Kivalina up on the northwest coast, even out on Little Diomede Island. That's what Little Diomede looks like from the Russian side. Little closer up in case you haven't been there, that's what it looks like. But those were geo satellites. That was the technology of the day. Nowadays, we have LEO satellites, low Earth orbiting satellites. And so those geo satellites were really helpful because it allowed us to provide what we then called modern telecom services to the villages. That meant everybody could have a telephone and a television set, right? That was modern telecom back in the day. But now everybody they not only want internet, they want broadband, they want high-speed internet. And so these new geo satellites can do it, but we have this new generation of LEO satellites that's really doing the job. In fact, I have a feeling that some of you have probably been reading about this because a lot of people in Alaska are, well, if you've been seeing antennas like this or like this on people's rooftop, there's a good chance that that's Starlink, right? And Starlink has been getting a lot of publicity. They are one of the companies that's doing LEO satellite technology, not only LEO, but broadband LEO. So a little bit, and this is maybe a little tutorial that some people are probably already familiar with, but the difference between GEO and LEO, GEO is geosynchronous Earth orbit. Those satellites are over the equator. They're at an altitude of 36,000 kilometers. And that's a really important altitude because that's the altitude at which the satellite goes around the Earth once every 24 hours. And the Earth rotates on its axis once every 24 hours. So that means that from a position on the surface of the Earth, that satellite is staying at the same point in the sky. If you could see it, it just stays at the same. In other words, the satellite orbit is synchronous with the rotation of the Earth. That's geo orbit. And so that's why those satellite Earth stations, like the one I showed you, don't need to move. All they need to do is point that beam at one point in the sky and it all works, right? LEO orbits are different. LEO orbits are, not surprisingly, much lower orbit, typically in several hundred kilometers altitude. So the GEO is 36,000 kilometers. The LEOs are several hundred kilometers above the surface of the Earth. And so that's kind of a little bit higher than the International Space Station, but it means they come around about once every 90 minutes, every 90 or 100 minutes. So the orbits are not over the equator. They could be over the poles like that. We call that a polar orbit, or that could be tilted at some other angle. So the LEO orbits are not, it's not necessarily any particular orbit. It might be a polar orbit, or it might be some other kind of an orbit. And unlike the GEO satellites, it takes many satellites to provide coverage, because with a GEO satellite, you could have one satellite continuously providing coverage on an area of the Earth, right? Just like I just described. But the LEOs, those are coming round and round. So a LEO might be within view for only 8 minutes or so. And so if you're trying to get connected, you might be connected to a satellite for a few minutes, but then that one falls below the horizon, and then you need another one. And so you need a lot of satellites to provide coverage. So this is a pretty good slide for explaining the difference between GEO and LEO, but there's one problem with this slide is it's not drawn to scale. This one's drawn to scale, and it really emphasizes the great difference between the altitudes. So you can see a LEO orbit there, and that one is 500 kilometers above the surface of the Earth. The GEOs, the black ones, are much higher at 36,000. So the main point of that is just to emphasize that. A little bit more about the GEO satellites. I said 36,000. It's actually 35,786. That's the altitude that provides that geosynchronicity. When it comes to data, they've typically been used for low speed service, although there is a new generation of GEO satellites called high throughput satellites that are capable of providing higher speed service, but traditionally they've been lower speed. And one thing that you can't change about a GEO satellite is latency. There's a delay in there because it takes time for a radio signal to go all the way up to the satellite and then be retransmitted back down to another Earth station. Even though radio travels at the speed of light, it still takes a quarter of a second. Has anybody ever talked on a phone call on a satellite link? If you have, you know what I'm talking about. You hear that delay. In fact, it might be well over a quarter of a second because some phone calls go through multiple satellite hops. Another one that younger folks might relate to would be TV news, where you have the TV anchor is calling in a reporter from far away and asks a question, and that it takes some time before that answer starts. We've all seen that, right? So that's because it's a satellite link. And once again, it might be a couple of satellite hops to get to the Middle East or wherever it is. And so it might take, and so it's not only the time for the question to go back out to the reporter, but then it takes more time for the answer to start to come back. So that's why you notice that satellite, right? But the latency also causes problems with data communication. It's definitely not ideal. The LEO satellites, on the other hand, are below 2,000 kilometers altitude. These new satellites that are coming out provide broadband, high-speed internet, and the latency is much lower because, well, the altitude is lower, right? So it doesn't take so long to go up and back to a LEO as opposed to a GEO. And as I said, it takes many satellites to provide coverage. It takes many satellites just to provide coverage of one point on the surface of the Earth, right? And then as long as you have all those satellites up there, depending on the orbit, you may also be providing worldwide coverage. You may be providing coverage at all latitudes, and we'll take a look at that in just a minute. But this is one example of a LEO constellation. This is a really old LEO constellation. It's one that's been around for 25 years. It's the Iridium constellation. And so if you've used a satellite phone or maybe a Garmin InReach device, you know, one of those devices that people use when they're out in the wilds, then the chances are that you're on the Iridium constellation. This was originally started by Motorola. Some of you might know the story. Motorola started it back in 1999. It was a huge technology success, but a business failure. So there were some smart investors that came back and bought the constellation from Motorola. They paid pennies on the dollar, and then they made the business case, and now it's an $8 billion company. So that's Iridium. And you can see that those satellites are in polar orbit. They go over the North Pole, over the South Pole, but in multiple different orbital planes that are all polar orbits. I made the point about covering every point on the surface of the Earth. So I've got this animation that shows you how Iridium is actually able to provide coverage everywhere. And so there are 66 satellites. Each one has a coverage area, which you see as a circle there. And then that means that every point on the Earth is being covered by at least one satellite. An interesting point about this animation, you can see the Earth rotating under constellation, which is pretty interesting. And sometimes people ask, how did Iridium get its name? That's an interesting story because originally, when Motorola designed this, the engineers used 77 satellites. So they went to the periodic table of the elements. Some of you are nodding, so I think you've heard this story. And the element with atomic number 77 with 77 electrons was Iridium. So that sounded like a great name. Then later they redesigned, we only need 66. And so they went back to the periodic table and the element was dysprosium. Yeah. So they just stick with Iridium. So that was the story on that one. But that's just an example of a LEO constellation. That's not a broadband system, right? That's a low speed. It does move low speed data. That's how your Garmin InReach device works, is it's moving low speed data. But now we've got some new companies that are on the scene, and these are 4 major ones that are using LEO satellites to provide high-speed data, to provide broadband. And the one that I think is probably what's known, at least here in Alaska, if not elsewhere, is Starlink. That is part of SpaceX, an Elon Musk company, a guy who seems to make the news a lot these days. They right now have about 6,800 satellites in orbit. They've got permission to bump that up to a total of 12,000, and they're proposing 42,000 total. Who knows? Maybe they'll go higher than that. Elon's a pretty ambitious guy. So that's one, and there are here in Alaska, I think Starlink became pretty well known when we had the quintillion cable cut up north, right? Because the people in those communities along the north and northwest coast had been intrigued by broadband being connected. They were now using the cloud, right, for a lot of stuff. So then when that cable cut happened, that was a pretty devastating. And inevitably, a lot of people just switched over and started to use Starlink, at least while the cable was out. And then who knows, maybe beyond, maybe when the cable came back, maybe they continued to use Starlink. Also, in lots of other parts of rural Alaska, people have been able to get broadband for the first time by using Starlink. OneWeb is another company that provides service in Alaska. They currently have 648 satellites. I think 600 of those are operational and the other are spares. They proposed a constellation of 7,000. And then 2 companies that are getting ready to provide service are Amazon. They call their constellation Kuiper with about 3,200 satellites, and then a Canadian company called Telesat with 198 satellites. And there are other companies that are coming along. There's one called AST that is a low Earth orbiting satellite company, but it is planning to provide service directly to smartphones. And so that's kind of another interesting story that we're not going to be talking about here, but lots of interest in this technology.
They just set one up here just last week, an AST.
AST, yeah, right. Yeah, AST was just in the news, just in the past week or so. A little bit more about Starlink. This gives a little bit of detail about their orbits. Starlink has 4 orbital altitudes between 540 and 570 kilometers. They go 540, 560, 540, 50, 60, and 70. With a couple different orbital inclinations, including that polar orbit that I mentioned. OneWeb is higher, they're at 12,000 kilometers, and their satellites are in the polar orbit that I showed you with Iridium. Just to define orbital inclinations, in case you wondered what that is. So the polar orbit is, we call that an orbital inclination of 90. Now on this picture, if you're looking at the Earth from a distance, then the equator is that horizontal line, and then the 3 other lines are what the orbits would look like. And if you look at them edge on, right, it looks like the orbital plane looks like a line if you look at it from the edge. So there you see the 3 angles. It's just the angle between the equator and the orbit, 53, 70, and 90. So when Starlink first launched their first group of satellites, they were at 53 degrees, which meant we didn't get much coverage here in Alaska because they weren't coming to a high enough latitude. But then later on, they also added the 70 and 90 degrees, and so now we have good coverage from Alaska. It wasn't completely arbitrary, I think, that they chose 53 degrees because most of the world's population is between 53 degrees north and 53 degrees south. So, you know, they kind of know what they're doing. OneWeb is, I guess I showed you the OneWeb. So the OneWeb orbits are pretty easy to describe. Those are all polar orbit, but at a higher altitude of 1,200 kilometers. A little more detail about Starlink. They're now providing service not only in the US, but in over 60 countries around the world. Nominally, it's 100 megabits per second, which is pretty good broadband service. I mean, I think you can get more, you can get higher speeds than that in the city, but that's pretty appealing to people that don't have any other option. But actually, people experience speeds more in the range down as low as maybe 20 megabits per second, maybe even lower in some cases. The reason is because the constellation only has a certain capacity. So it's just like the way the cable TV companies used to provide internet service where you were sharing capacity with your neighbors. You know what I mean? So in this case, your neighbors may be, you know, in your state or your part of the world, you're all sharing capacity. So that's why your actual speed may vary. But then the latency is way lower than that quarter second that I talked about for the GEOs because the LEO is much lower and the signals don't have to travel so far. Their business model is interesting. You can go online and order the equipment and the antenna directly from Starlink, generally no human contact at all. This is Elon Musk, right? You order your stuff, they send it to you and it self-install. Although if you need help with installation, I think there are some companies that will help you with that. Pacific Data Port, will they help you with the
microcom side does.
With microcom, always get those two confused. And I think there are companies that will help you with that installation, but I'm pretty sure everyone in this room could handle that very nicely without any help. There's a Starlink antenna, a user antenna, and this is an example of a flat panel antenna. And interesting thing about this is, I talked earlier about how the parabola focuses a beam. That can do the same thing. In fact, that's where my colleague, the good Dr. Monk, is going to talk a little bit more later about those flat panel antennas. A little bit about Starlink's prices and so on. The residential service is $90 a month, and you also have to buy that terminal. That's one time. If you do self-install, one time for the terminal and the antenna, and that's $5.99. OneWeb, the data I have indicates that their user terminal is capable of speed of 195 megabits per second, downlink 33, uplink. But once again, that's capacity limited. So it has so the speed that you actually experience has very much to do with the capacity of the constellation and the traffic level that's going through there right now. Latencies roughly the same, although maybe a little bit higher because the OneWeb satellites are in higher orbit. They have a different business model than Starlink. Starlink, as I said, provides service directly to your residents. But OneWeb is more oriented to what they call the enterprise customer, which would be a company, or in the villages, it might be a school or a clinic, something like that. Or another option for them would be to provide service through an internet service provider. And so in that case, the internet service provider would provide distribution within the village, and then they would use a single Starlink terminal to provide the connection to the internet. And the OneWeb is represented in Alaska by Pacific Data Port, right, Sean, or Microcom with Pacific Data Port?
Several companies.
And then ACS, and I think there are probably some other companies that are able to represent OneWeb at this point. I showed you a Starlink terminal. A web terminal is a little more substantial, and this is one example of a OneWeb terminal. Underneath those radomes are parabolic antennas, right? And we talked earlier about how a parabolic antenna can focus a beam, but if you needed to track the satellite, you're going to need to move that parabolic antenna so that the beam follows the satellite. So you've got a parabolic antenna under each one of those radomes, but you need two parabolic antennas. You need one to move traffic while the other one's looking for the next satellite. So if you imagine the antenna on the right is moving data, serving customers, the one on the left might be looking for the next satellite, and then when it becomes necessary to do the handover, then it switches. And so then at that point, the antenna on the left would be moving traffic, and the one on the right would be looking for the next satellite. Interestingly, I think that OneWeb is also coming out with a flat panel. Jens is going to talk about flat panel antennas, but I think they have a flat panel antenna that can do everything that I just said. In other words, a single flat panel that would be able to do both things.
Yes,
Is that right, Sean?
we have one that's all in office. Yeah.
So that's all kind of the good stuff that's happening, right? But what about the challenges? And so there are three big challenges that people are talking about. The first one is light pollution, because these satellites reflect sunlight. They can reflect sunlight, and that means that you might see them from the surface of the Earth. In fact, they might be pretty bright. In fact, here's a picture of a train of Starlink satellites on their way to orbit. And here it is in motion. So when I travel outside, a lot of people are telling me that they saw this, and it really got their attention because, I don't know, and I think even with the lights on in the room, you can see that those are brighter than the stars. So astronomers don't like that very much. And other people don't like it very much, other, amateur stargazers and other people that just like the night sky. So to be fair, those satellites are on their way to orbit, they are not in orbit, right? So I guess you could say this is temporary in the sense that they're pretty bright when they're on the way to orbit. When they're in orbit, they are not going to be reflecting as much light as that, but still they are reflecting some light that astronomers don't like. So as far as the solution for that, about all I know is Starlink says that they're working with the astronomical community to configure their satellites so they don't reflect as much light. So we'll see how that comes out. In the meantime, the next major issue, and I was actually talking to Scientific American magazine yesterday, and they and other news media this is the one that they're really covering, is the space debris problem. Space junk. There are lots of objects flying around up there, right? Especially between 500 kilometers and 1,000. And it's not only these satellites, there are lots of other objects out there. So it stands to reason that as we get more and more objects in this space, at some point there's going to be a collision. In fact, there already have been collisions. So there have been some small collisions. There have even been some big collisions. In fact, Iridium lost a satellite in 2009. There was a collision between an Iridium satellite and a Russian satellite. And so I've been in the Iridium Network Operations Center, so those guys were watching their screen. All of a sudden, one of their satellites disappeared. And it took some time to figure out what happened, but what happened was there was this collision that I described. There is the ability to steer some objects and avoid collisions, and that happens. But there's also concern not only about collisions, but also about a chain reaction. So you could imagine where two objects collide, that throws off debris, and then that debris strikes other objects, and that would be a catastrophic event, I would say. It's sometimes called the Kessler effect. So if you hear about the Kessler effect, that's what people are talking about. So the risk seems to be, and I'm still looking for someone that's actually quantified this risk. It's a little bit hard to figure out because there are objects of different size. I think NORAD tracks objects down to 10 centimeters size. So it's a little bit hard to quantify, but the sense is that we haven't gotten to that catastrophic situation yet, but there's definitely a risk as more and more objects are up there. And there was actually a movie about this. Did you see the movie Gravity? So that was the theme of this movie. Okay, so that's light pollution and space debris. The one that Jens and I have been working on is if space debris is congestion of space, radio interference is congestion of spectrum, right? Radio spectrum. And radio spectrum is becoming a pretty valuable resource. So there's a concern about radio interference between LEO and GEO satellites and also among LEO satellites. And the reason that is particularly a problem is because the regulators have assigned both the LEOs and the GEOs to the same spectrum. And I mean exactly the same spectrum. So if you've worked in radio, you might think, well, everybody's got a license, they've got their own channel, right? And that's the way it works with some services, but not with these. With these, they are literally in the same spectrum, but they're not supposed to interfere with each other. So, and the spectrum I'm talking about, these are the bands where LEOs and GEOs are assigned to operate in the same band, KU, KA, and B. And there's also a new FCC order, you may have seen this, Sean, at 17 gigahertz, a new band at 17 gigahertz, where the expectation is that both services will share the band. So you might wonder, how do they do that? You know, and that's pretty much what we've been working on. How do they share the band? But what brings it about in the first place is that the regulating agencies in the US, we have the FCC, and then at the international level, there's the United Nations International Telecom Union, ITU, they call it. Both of these, well, ITU makes kind of the worldwide guidance, and then in many cases, the national regulatory agencies like the FCC will adopt the ITU's guidance. And so in this case, 2 points. One is the LEOs are not supposed to interfere with each other, right? Now, again, how is that going to work? You know, well, the FCC has said, in effect, you guys work it out. The FCC is asking that the LEOs, when they're sharing the same spectrum, that they sign agreements that detail how they're going to share that spectrum. Interesting. The FCC does have a default plan, which is a little hard for me to understand, but they do have a default plan. If you can't work it out, then we want you to do this. But really, the preference is that the LEO companies themselves figure it out. In addition to that, what about the GEOs? You have the GEOs up here at high orbit and the LEOs at low orbit, but they're all sharing spectrum and they are all at some times serving the same general regions on the surface of the Earth. So you could see how they could interfere with each other. So in the world of radio regulation, we have the idea of primary and secondary carriers. So the primary, so in this case, the GEOs are primary. That means they were already there. They were already operating. The secondaries are the LEOs. They're the new guys. So they're required to protect the primaries. So the way this plays out then is the GEOs don't have to do anything different than they've already done. The LEOs must make arrangements so that they don't interfere with the GEOs. And there are ways that they can do that using beam steering. And it turns out it's not too hard, but it is a requirement for them to do that. And I've already mentioned the radio bands that are in play here. So let's talk about how interference could happen. And so this is the thing that Jens and I have been working on with some of our colleagues at Carnegie Mellon in Pennsylvania. So one way to think about this is that you have a GEO Earth station that is communicating with its GEO satellite. And as we've said, that GEO Earth station doesn't have to move, it just keeps pointing at that satellite. Then you have a constellation of LEO satellites and, whoops, sorry. Then you have a constellation of LEO satellites. And this, here I'm only showing one satellite, but there are really lots of them up there. And so at some point, this satellite or some other LEO satellite is going to be at a position that's directly in between the GEO Earth station and the GEO satellite. Okay? So you can imagine that if that happens, and the GEO Earth station is pointing straight up, and if the LEO satellite is pointing straight down, and if they're on the same frequency, then you could imagine that there would be interference, right? Okay. So that is kind of a simplified way of thinking about this. And so you'll hear people talk about an inline event, and the problem is an inline event. But actually, it's a little more complicated than that. And the reason it's more complicated is because antennas, and here we talked about a parabolic antenna, which has a beam, right? So we could think of that beam that's being projected from that antenna as a cone, right? It gets, this cross-sectional area gets bigger as you move farther away. So we could think of it as a cone, and we could think of that the radio energy is being concentrated on a beam within that cone so that a receiving station that's within that cone would be able to pick up that signal. Right? That's one way to think about it, right? So this is kind of a simplified concept of how to think about things. Satellite earth stations and satellites, they don't only transmit, they also receive. and using the same antenna typically. So now if this same antenna is receiving, that means this cone represents its, you might say its reception area, right? In other words, it can receive a signal from a transmitter that's within that cone. So it's kind of this antenna's region of sensitivity or receptivity, right? So the pattern of this antenna is important both for transmitting and receiving. So now let's go back and think about how could you get interference between a satellite and an earth station? Because satellites and earth stations both transmit and receive. So that one way that could happen would be if the transmitter and the receiver are both on the same frequency and polarization. We're not going to talk about polarization here, but that's another factor. And if the transmitting cone intercepts the receiver, in other words, if the receiver is within that cone, and then if the cone of the receiver intercepts the transmitter, then there could be a problem. And so that's a way to think about it. If the receiver is within the transmitter's cone, and if the transmitter is within the receiver's cone, then you could get interference. But as you'll see in a minute, that interference can be avoided if we do beam steering, if we point the beam in a different direction. So here's an example. And this is just going to be one example of many examples that I could show you. But just to keep it simple, we're just going to talk about LEO to GEO interference on the downlink, right? So we're just going to talk about that case that I mentioned earlier where a GEO earth station is trying to receive, but there's a LEO in the way, and if that LEO is pointing its beam down, then there could be an interference problem. There are a lot of other cases. There's uplink interference, there's LEO to LEO interference, but this is just one of the possibilities. So here is the inline event again, right? The GEO satellite is communicating with the GEO earth station, and then there's a LEO satellite in between. And if that LEO satellite is pointing its beam straight down, then you would think that there could be a problem. And shown this way, we see the cone of the LEO satellite intercepting the GEO earth station. The GEO earth station's cone will be intercepting the LEO satellite. So that's where there could be a problem. So that is an inline event. But here's another inline event where in this case, everything's the same except the LEO satellite is pointing its beam in a different direction. And so now the cone of the LEO satellite does not intercept the GEO earth station. So those could be on the same frequency. And in this model, in this way of thinking about things, that avoids the problem. Here's another problem with the inline story. Let's see. Here's a GEO satellite and a LEO satellite where you do not have an inline situation. Okay. And so here's a picture of the GEO earth station. The LEO satellite, although it's not in line, it's still close enough to inline to be intercepted by that cone. And similarly, the LEO satellite's cone intercepts the GEO earth station. So that's not exactly an inline event, but it's an event where interference could happen. So this is a way of thinking about things to try to, first of all, analyze when interference can occur. And then once we understand that, it helps us to think more about how to avoid that interference. And it all comes down to beam steering. One other thing, and this is the setup for Jens, okay? One other thing is, in real antennas, there's more than just the main beam. There are also radiations in other directions that we call side lobes. So here's a different situation to think about. And in this one, it's definitely not an inline event. This LEO satellite has its main beam is going straight down, right? let's say it's transmitting straight down, and the geo earth station is pointing straight up, so it's receiving straight up. So if you put the cones on that one, you'd say, oh, there's no problem there. But actually, in real life, real antennas radiate in other directions, not only the main beam. Jens is going to show this to you in a minute. So if the LEO satellite were putting out some radiation in this direction, maybe just a little bit of radiation, but some radiation, and the GEO Earth station is capable of receiving not as well as in the main beam, but still receiving a little bit, having a little bit of sensitivity in this direction toward the GEO satellite, then there's a little bit of energy that can be received at the GEO Earth station, a little bit of energy. Now, is that a problem? Well, probably with the number of satellites that are up there right now, probably not. But if we have 40,000, 60,000, some experts are predicting we'll have 100,000 LEO satellites. I don't know if that they take care of the space debris problem, right? So if we had 100,000 satellites, then we actually have run the numbers and found that yes, there are some issues when you get up to those number of satellites. And so that's why the side lobes are important. So at this point, I want to switch you over to Jens. And Jens is an antenna expert. So Jens is going to talk about the real world of satellite antennas.
But I'm not a telecom expert, I should add that. So, did you realize it was Friday the 13th today, Alex? I hope this isn't bad, so, okay. So let me get started with my slides here if I can. So I'm going to talk about antenna radiation patterns. This is something that we do a lot of calculations of in antennas class that I teach. So we deal with kind of dipole antennas, aperture type antennas, horn antennas, dish antennas, and probably most importantly, antenna arrays, which end up being some really interesting. You just have so much flexibility with antenna arrays. So what I've plotted here is the radiation pattern from a typical dish antenna, and here I'm, I am.
The one on the left is that.
Okay, here we go. I think I'm hitting the wrong button here. So what I'm looking at here is a dish antenna with a diameter of 4 wavelengths. So for example, if I measured that diameter, the important number here, when you want to know what the radiation pattern is doing, is how big is that dish? Not in meters, wavelengths. What frequency are you transmitting at? And so the bigger that dish in terms of wavelengths, the more focused the energy. And you will hear antenna engineers, if you ever get a chance to hang out with an antenna engineer, they'll talk about the directivity or the gain of the antenna or the beam width of the antenna, and they're all kind of describing the same things. How well does this antenna focus its power in a certain direction? And so the higher the directivity or the gain, the more focused that beam is. And likewise, the narrower, what we call the beam width of the antenna. And so this very first plot, I'm showing you just on a linear scale. What I'm showing you here is the power density of this antenna, assuming this it's radiating in this direction here. I've kind of turned it sideways so you can see it radiating like so. So this is normalized. The power density here is 1. And then you can see as you move off that angle there, the power density decreases very quickly. And I have a scale here, 0.2, 0.4 up to 1. So 1 is going to be the maximum power density. So 0.5, which would be somewhere in here, would be the value where if you're below that, the power density being radiated is less than half of the maximum amount. So we actually, if you imagine me drawing a circle here at 0.5, if I measured that angle from the center to that point, that would be what we call the beam width of the antenna. So if you're within the beam width, your power density is always greater than 1/2 of the maximum. If you're outside of the main beam width, you drop to below that. And you see in this case, your antenna, the power density drops off pretty rapidly as you get off the main beam. So this is a linear scale, and it's one way of showing what antennas do, but a better way to show what antennas do is to take the log of this and express it in dB, because we can see there's actually stuff going on here, low-level stuff going on that doesn't appear very clearly in a linear plot, but would if we plotted it in dB. So that's what I'll do next. So here's the exact same antenna pattern in dB, and all of a sudden it's like, wow, it was doing that. And so what Alex was referring to are some of these other directions where this antenna radiates. These are called side lobes. And here, even though this beam looks a lot fatter than it was before, it's actually, it's the exact same radiation pattern as the one I showed you before. In this case, the beam width of the antenna is going to be, if we express it in dB, it's going to be that point where it drops to 3 dB of its maximum value. So here I've normalized the maximum to 60 dB. So if I go 57 dB, it's somewhere in here, I would get exactly the same beam width I got before. So if you're outside of that angle, your power density has dropped to less than 1/2 of this maximum. That's what a beam width is. Okay, so the other thing I would point out is your side lobe, your first side lobe turns out to be, if you look at this, it's 17 dB below the maximum. I think the next one's around 25 dB below the maximum. And what does 17 dB mean? It means that the power that this antenna is radiating in this direction here is about 2% of the maximum. So the reason we didn't really see it before was on that scale from 0 to 1, we're looking at 0.02 and it just doesn't show up. Now we're in dB, so this one right here is 25 dB less than the maximum. That turns out to be 0.3% of the maximum. So these are very low values. And as Alex alluded to, do they matter? Maybe. It depends, but they're there and you need to be aware of it. The other thing that I should mention that Alex alluded to, whether you're transmitting with an antenna or receiving, they have the exact same pattern. So if an antenna transmits really well in a certain direction, it receives really well in a certain direction. And you notice in this pattern, there's actually things we call nulls. Like in this direction here, your antenna doesn't receive or doesn't transmit anything. It does, if you move over a little bit, you get this side lobe and you would get some energy transmitted in that direction. But in this direction here, if I were using this as a receiving antenna, I wouldn't receive any information. I wouldn't receive any energy either. Okay, so this is something actually I just covered in my antenna theory class. We have a theorem called the reciprocity theorem. We actually proved that antennas transmit and receive in the exact same ways. So there's not a separate transmit pattern, or wait, you're using that as a transmit or receive, it's the exact same pattern. So everything I'm showing here is identical. Okay, so if I increase the diameter to 8 lambda, here's the linear plot. I don't know if you can tell, if I go back, you can see that 4 lambda, 8 lambda, you see how it's getting narrower. So my beam is definitely getting more focused. So this will be the last thing I'll show in linear. Here's my antenna beam now in dB. And one thing that you'll notice is, yeah, this is definitely narrow. But the other thing is there's more side lobes than there was before. They're kind of getting squeezed together. But the level of the first one is still minus 17 dB. The next one is still minus 25. And so what happens as you make your dish larger, you focus your beam, you actually are increasing the number of side lobes, but they're getting small quickly. Okay, so just carrying on with the story here, here's 16 lambda, 32 lambda, starts to get kind of interesting. I mean, this is a really, really narrow banded beam right here. And so, you know, if you have a 1 meter antenna, and you kind of want to know something about the radiation pattern, well, figure out what frequency you're transmitting at. Frequency times lambda, the speed of light, find out what the wavelength is, find out how many wavelengths a meter is at the frequency you're using, and you'll have a good idea of what the radiation pattern looks like. So this is kind of a little discussion of parabolic dish antennas, and they are great for a lot of things, particularly if you're looking at a geostationary satellite and you don't need to move the antenna. Okay, but if you need to move the antenna, you know, parabolic dish may be fine, or you may need something a little more sophisticated, like a phased array. And so I'm talking a little bit about phased array antennas, and actually phased, well, an array is just a systematic grouping of antenna elements. Okay, and you can arrange your array in a rectangle like this one right here, or in some sort of circular I guess circular array like this one right here. I think this one is actually a Starlink antenna, and this is actually from the Starlink patent for their phased array antenna. And it's kind of interesting because these guys right here would be your little antenna elements. So instead of having an aperture, you basically have a bunch of little antennas that you arrange in some sort of periodic manner. So what's so good about phased arrays? Well, the most important advantage of a phased array over a parabolic dish antenna is your ability to electronically steer it. And that means you can steer it very quickly, which you couldn't with a mechanical steering system. But think about an antenna on a satellite where you might need to redirect the beam. Parabolic dish is out of the question. You rotate the antenna, you're going to rotate the satellite, right? And as soon as the satellite runs out of fuel to be able to do those little minor corrections, it's spent. So parabolic dish on a satellite is fine if you never have to change the direction. If you need to steer the beam, it's got to be a phased array. The other thing is, and I think Sean, you might have alluded to this, the multiple beam steering. With a phased array, you can send multiple beams in multiple directions, and that means you can transmit or receive in multiple directions simultaneously. So that picture that Alex showed earlier of the two parabolic dishes, where one of them was tracking a satellite, where the other one was looking, you don't have to do, you can, one antenna can do both of them. And it's kind of cool. You just calculate, you know, what do the current distributions on your array have to do to point that way? What do they have to do to point that way? Add the two solutions together. It just becomes superposition and super simple. All right. Now, the other thing you can do is improve slide lobe control. So what I showed before was that those side lobes at minus 17 dB. That was that first side lobe, and they're just, you know, there's no getting around it. You don't have a lot of control with a parabolic dish antenna. But with an array, you can actually taper it so that the currents on the outer part of your array are less than they are in the center. So you can kind of gradually taper the amplitude of your currents for all these little antennas on your array. And if you do that, you can theoretically knock down the side lobes to 0 or minus infinite dB. You can completely get rid of them. You do like a Gaussian taper. Now, I'll show you an example, but you all know in engineering, there is no free lunch. So what do you pay? Well, except for on Fridays. Friday the 13th, no less. So I was going to show some examples of some phased array plots. So I wanted to show you this one. So this is a simulation that I did for an array of little half-wave dipoles that I put together in a 4 lambda by 4 lambda circular pattern. And I know you all remember what the 8 lambda dish looked like. You're like, hey, it looks exactly like the 8 lambda. So it's identical. So, you know, you wouldn't build an array antenna if you didn't need to do something else with it. But if it's the same size as your dish, in this case, assuming it's 8 lambda, I could plot these 2 radiation patterns and they would just plot right on top of each other. Exact same pattern. But I've already mentioned things that I can do with an array that I can't do with a dish that I can't do with a dish antenna, and that is to steer the beam without actually physically rotating the antenna. And the way you do it is you kind of adjust the phase of the elements in some sort of progressive way. So instead of adding constructively in one direction, they add constructively in another direction. And so that's kind of what I want to show here. So here I'm looking at a 16 lambda array in a circular pattern. And what I'm going to do is progressively change the phase in some sort of linear progression across the face of the antenna. And what you can see is I can now steer the beam. Here I'm doing a 20-degree beam steering, a 40-degree beam steering. And so the other thing I think that you notice is that that side lobe is, oops, I hit the wrong button, Alex. Hold on. Your side lobes are not really affected by your beam steering. They're still a fact of life, unless the last slide I'm doing is I did a little taper. So this is that 8 lambda circular aperture, but in this case, I have tapered the currents so that they're less on the edges than they are in the center. I applied some sort of Gaussian taper. And so I said there's no such thing as a free lunch. This is where I was getting at, Alex. The beam is fatter here than it was before. So, but the side lobes are really low. So before they were minus 17 down, which is like right in here. Now they're about minus, I don't know, almost minus 30 dB down, which is really, really low. I mean, minus 30 dB is 0.1% or even maybe less than that. It's 3 orders of magnitude below the main beam, or the other side lobe, when we didn't do any tapering, was 2%. So this is significantly lower. So if side lobes are a problem, you can get rid of them, or you can alleviate it by, again, tapering the current elements on each, tapering the current magnitudes on each of your elements. If you also need a really narrow beam, then you're just going to have to make your array larger. And I think that's all I have, Alex.
Okay, great.
I'm ready to throw it to you.
We're almost ready for Q&A, and I think we're doing okay on the time. They told me we could run a little over if we need to. So I mentioned that we've been working on a lot of this with our colleagues at Carnegie Mellon. So in case anybody's really interested in this, I'm giving you the information on some papers that we've published. The first one here is, well, they're both looking at the LEO to GEO problem, the one that I illustrated a few minutes ago. And so it says mitigate KU band LEO to GEO interference. So the one on the bottom here was published 2 years ago in 2022. And that one is just looking at the main beam. In other words, the story that I told you. And then the one from 1 year ago, July 2023, that one is looking at also considering side lobes. And what we found was, using some real world data, we found that side lobes are significant to this problem when you get up into the range of 30 or 40,000 satellites, which we don't have right now, but could happen in the future. So in case you're interested, you could look it up. These are published in IEEE Access, which is a freely available, anybody can bring it up, you just get it online. So that's our story, and we're sticking to it. Any questions or comments?
I have a question. Just what's the satellites that are in LEO, lower further, what sort of bodies are they broadcasting?
We usually talk about EIRP, which is a way of characterizing the effective radiated power, and it's effectively a watt, 1 watt. Are you thinking about those solar panels and how much energy it takes to? Yeah. I haven't really tried to think to crunch those numbers, but we are talking in terms of EIRP, we're talking about each beam being effectively a watt, but what that does is that factors in the gain of the antenna, right? So EIRP is what transmitter power would you need to get this signal strength if the antenna were radiating equally in all directions, which it's not, it's focusing a beam. So that's why we call it, it's actually effective isotropic radiated power. So in other words, I don't really have a real good answer to your question.
You don't have plate power.
Right. Any other part? I think what Jens is talking about is really interesting. I think you could mitigate that side lobe problem if it turns out we have enough satellites for it to be a problem, by basically working with your antennas and either knocking those side lobes down or something like he described. Was there another one over here?
I was gonna say, I can tell you that the amount of energy that they push towards Earth is the maximum they can get away with, in all cases. And there are signal density limits, imposed by ITU and the FCC. But, having worked through building a satellite, I can tell you that we try to license it for the maximum amount of power that we could put on any one point on Earth, right? And with phased array systems, it's really important because you could take your entire, the power that you have available to your satellite, and you could focus it into a very small, into a small area, or you could spread it out over a very large area, and those signal density differences are huge.
Sean, do you have an answer to how much power it takes from those solar arrays to power them?
I can tell you that the small sat that we designed was in the 1.5, 1.7 kilowatts total consumption, but the large spacecraft, those things are power hogs, right? I mean, they do. They have some very large transmitter arrays, and they use a lot of power. And part of that is because they when they go dark, right, when the sun's behind the Earth, right, is they're building up those reserves in the batteries, right? So
This is Sean Fitzpatrick. If you don't know him, he's engineering VP with Pacific Dataport, and he knows what. You can tell me later if I got anything wrong, okay?
just one picture that wasn't really a Starlink thing.
Okay, yeah, Ken.
One comment and one question. Starlink's raised its consumer prices since you did that. It's
Oh, really?
it starts out at $120 now.
$120 a month? Because they were at 100, then they went down to 90,
Yeah.
and now they're up to 120. Okay,
Yeah.
we'll fix that slide. Mhm.
So my question is on the phased array. Jens talked about the adjusting the current elements. So I guess I missed the pointing is just done by element by element.
Right, adjusting the phase relationship.
I can probably scan through and show you the picture of the array and show you what you kind of have to do. I mean, see if we can get there. I think we have some latency here.
Yeah.
So if these are my array elements here, if they're all in sync with each other, what's going to happen is if I'm standing right in front of this circular array, that beam is going to come right out because everything is going to arrive at the same time. But if I want to direct the beam, let's say in this direction here, what I'm going to do is adjust the phase of all the elements along one line to be the same. and just progressively adjust the phase so that things are, so this has nothing to do with the amplitude of the currents like on these little elements, it's the relative phase to each other. So now, instead of adding constructively in this direction, they'll add constructively in this direction because these things are a little delayed in time from each other progressively. So now things, yeah, they're just adding constructively in a different direction. Does that?
Yeah, that answered, thank you.
How about John?
I had a follow-up to that, so how do you actually do that, is it like pair actors or?
See that thing right there?
Yeah,
It's actually, this is where your expense is for a phased array. I mean, doing what we call an array is not necessarily that makes it, it's that the circuitry and all that stuff required to kind of do these phased arrays. And to be able to do it, to have the flexibility to kind of do anything you want. Are you guys all familiar with the HART facility in Gacona? That's actually a phased array. It's used to kind of study the ionosphere, and it literally throws up enough power to ionize the ionosphere and to create your own aurora. That's a phased array, and it's just incredibly flexible. You can do anything on that array. And we've even done experiments where we adjusted the phase of each element. So if you look at if you divide the array into 4 quadrants, any element here, we would have 180-degree phase delay with the element across from it. So if you go around circle here and you're looking right at it, there's always cancellation straight ahead. So we create what's called a twisted beam, but these are, I mean, nothing you'd ever want to do in communication. But with these antenna arrays, you can literally do anything with the beam. Like I said, you can send beams in multiple directions. You know, if you have the flexibility to individually adjust the phase of each element with respect to the others, you can really do all sorts of crazy cool stuff.
I have one phased array story in history, right? So John and I both once worked in AM broadcasting, and in AM broadcasting, the antenna, the tower is the antenna. Tower isn't holding up the antenna, the tower is the antenna. And so I once worked for a radio station which was outside New York City, but its audience, they wanted to serve that New York City audience. So they used what's called an end fire array, and it was a series of 5 towers, really high towers, right? And they were all in a line, and the phase was arranged so that the signals arriving from all of those towers all aimed toward, it all went toward New York City, and the signal just pounded into New York City. The New York City guys didn't like it too much. Okay, yes, Kim.
So 2 more kind of separate but related, talked about Iridium being 25 years old. What's the expected life out of those
Oh,
spacecraft?
I'm on board of Iridium, so I know a little bit about that. We replaced the satellites about 5 years ago. So we launched them on SpaceX, which both launches our satellites and competes with us. And they went up 10 at a time. I've got some pretty cool video of the launch and everything. And so they went up 10 at a time into a so-called parking orbit. And then they went up one at a time and replaced the satellite, and the other one was deorbited. Oh, by the way, as a board member, they have plaques on these satellites with our name on it. So I've got a satellite with my name on it. And my friends told me I'll be in space until I'm deorbited.
So you made me think of something else. You can actually go, if you want to send a payload by SpaceX, you can actually go to their website and get a quote from the website. You're talking about.
Right, no human contact, right? We got a question over here.
Yeah, so I understand, because knowing what I know about combat, and I don't know a lot, gotta be honest, my RF understanding is probably not where it ought to be. But my understanding is that higher frequencies, especially up in the more, as you get above the Ka band, they start to attenuate more in the atmosphere, especially as you got more moisture, rain, and everything else.
Right.
What's the highest practical frequency that could be potentially used in Earth satellite communications.
It's way up there. I had V-band is seriously, so we got, right now, there's a lot of use among satellite carriers of Ka band, which goes up on 30 gigahertz and down on 20, and then V-band is above 50 gigahertz. Sean, do you know anybody that's actually using V-band?
Yes, and in multiple cases, they use redundant earth stations on the ground to avoid weather instances. So they've got a network build where they actually switch between receivers and transmitters. So you got multiple earth stations that are 50 kilometers apart or so. And that way, if you've got an atmospheric condition in one area that would degrades, they can switch all those signals over to the other.
So it's
that's
pretty high
cool.
frequency.
So they're using ways on the ground to overcome the problem, but you are correct. The higher the frequency, the more attenuation you have by primarily water vapor in the atmosphere.
Okay, any others?
Yes, sir.
Is there interference, will this whole satellite network go down tonight when there's this big geomagnetic storm that hits the earth? Causes the aurora?
Oh, yeah, that's a good one, yeah, especially GPS. The one to really worry about is GPS because all kinds of systems are synchronized on GPS. But I certainly those electronics up there in space are vulnerable. Do you have any, so I guess, I mean, we talk about hardening in our equipment on the ground. They must be doing something up there. What do you say about that?
There's heritage flight components, and they call it heritage. It's been flown before, and yes, the more hardening you get, of course, the higher the price goes. So it's a balance of
Yeah, it's
how much do we harden.
it's definitely an issue. Any others?
That was hard to get. Lead shield.
A lot of shielding, yeah, a lot of shielding, potting where they put stuff inside of, because there's other stuff like 10 hairs and stuff that grow in space and all kinds of things that like to take electronics out.
Okay, well, these are great questions. Thanks. Have some lunch and Jens and I will hang around if you want to talk some more. Thanks.
Yeah, so I wanted to just say that the password group day survey is challenges, plural challenge, right? Plural of challenge, challenges, and they get an S. And let's give it up for our hosts and thank you so much, Alex.
Was that?